Pope from Winchester Grammar School for Boys, and today in the Recreational and Competitive Mathematics session 8 we're going to be looking at the British Mathematical Olympiad 2018. Same as last time, it's 3.5 hours. Full written solutions are asked for here, with complete proofs and so on, with any assertions you've made. Marks awarded on clarity of your presentation, stuff like that. And then the rest really is a bunch of suggestions. Really good competition. So 3.5 hours. Let's get my timer up. I find that the explanations by University of Bath are pretty good, explaining what's going on. And to be honest, what they're talking, I think they managed to explain the questions really well in 5, 6 to maybe 10 minutes max. But I think they skip, their solutions. They're not supposed to be, this is what you need to do. They're not a mark scheme as such, so I wouldn't expect them to say this is what you need to write for full marks. But it's more, this is how you'd solve the problem. I'm going to try and write out more formally what you'd need to do here for full marks. But again, this is just my opinion, and it's most probably wrong. But you do need to be thinking more along these lines when answering these kind of questions. So, okay, 3.5 hours. Question 1. A list of 5 two-digit integers is written as increasing order on a blackboard. Each of the 5 integers is a multiple of 3, and each digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 appears exactly once on the board. In how many ways can this be done? Note that a two-digit number cannot begin with the digit 0. Okay. So, question 1. So, is this even possible? Okay, so since the sum of the numbers from 1 to 9 equals to 45, and 45 is divisible by 3, then this is possible. Okay, if and then there's 10 digits, so we can make 5 pairs. So using each digit once isn't a restriction. So what I'm trying to say is there's 10 digits. To make 5 pairs, we can do that with 10 numbers. That's not a problem. It's not like we're running out of numbers to add. And the sum of all those numbers, and technically we're adding up to 0, right? So it's from 0 up to 9. Then because that sum equals to 45 and 45 is divisible by 3, then it is possible. Because if I've got 5 numbers, each divisible by 3, then their digit sums are divisible by 3, and then that essentially means all 10 digits summed must be divisible by 3. I mean, it's a bit of a baby point, but if for a number to be divisible by 3, for it to be in the 3 times table, then the digit sum of that number has to be divisible by 3. And now if you've got 5 pairs of numbers, 2-digit numbers, where each of those, you've got 5 2-digit numbers that are made up a pair of digits ranging from 0 to 9 where they're not repeated, then each 2-digit number, for each of those 2-digit numbers to be divisible by 3, then that means the sum of each of the 2-digit numbers must be 3. So that means the total sum of all 10 digits combined has to be divisible by 3. And in this case they are. Numbers from 0 to 9 up to 45. So that's divisible by 3. Okay, fine. So it is 100% possible. Next up, I want to consider the combinations. So I'm going to temporarily ignore restrictions. Okay, now so what I'm going to do is for the 2-digit numbers, I'm going to consider the first digit. So I can't start with 0, so I'll go 1, and then 2, 3, 4, 5, 6, 7, 8, 9. And then I'll map that onto the sequence of digits of what I can have for the second digit. So ignoring restrictions at the moment. What's all the possible outcomes? Okay, so if I start with a 1, then for it to be a 2-digit number divisible by 3, then the second digit can either be a 2 or a 5 or an 8. And I realise that 1 is the same as a multiple of 3 and then add 1, or a multiple of 3, let's suppose that n starts off at 0. Then technically if I make an n column like so, this is n is 0, 1, 2, 3, 4, 5, 6, 7, 8. And then the 9th one, I guess, well, I don't need to go that far. Then 3n plus 1 is n, 3n plus 2 when n is, well, no, I don't need to do this, do I? No, I'm being silly. This is when n is 0. And then when I have 3 n plus 3, which is a multiple of 3, so I'll just leave it as 3n. Now I'll make this a 1. So this is a 1, this is 3n plus 1. This is a 1, so this is 3n plus 1. 2, sorry, this is a 2, so we've got 3n. This is a 2, 3n plus 1. This is a 2, 3n plus 2. And this will be a 3 when I'm at 3n. So really, in terms of multiples, these should be the same, because they're the 3n plus 1s. These are the same, because they're the 3n plus 2s. And these are the same, because they're the 3n's. So if I just work on the first batch at the top, up here, just have to be very careful with some special cases. What do I have to add to 2? Well, I could add a 1, I could add a 4, and I could add 7. And for the 3, I could only add a 0, 6, or a 9. Now the oranges are all going to be the same, so they're going to be a 2, 5, 8. This is going to be a 2, 5, 8. The greens are going to be the same, 1, 4, 7, 1, 4, 7. And the yellows are going to be the same, but you have to be careful, they include themselves. So technically this is a 0, 3, 9, and this will be a 0, 3, 6. Okay, so without restrictions, it doesn't look like there's that many numbers. And indeed there shouldn't be, because if we're thinking of the 2-digit numbers that are divisible by 3, then I'm just looking at, well, what's the lowest 2-digit number? That's 12, up to the highest digit number, which is 99. So really, 99 minus 12, 7, 8, and then divide that by 3, 87 divided by 3, 3's into 8, go 2, remainder 2, that's a 9. But then I want the number of digits, so you add 1 to that 29, so there should be 30 numbers. And it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's only 27 numbers here. I wonder where the other 3 have gone. Well, I'm pretty sure those 3 numbers have to be 33, 66 and 99. The clue is we can't have 99 because it's the same number twice, and we can't have the 66 and 33. If I put down any other digit doubled, it's a multiple of 11, but not necessarily a multiple of 3. So yeah, we're only going to have 27 choices, but arranging them not going to be easy. So what do I notice? Well, I actually notice that the green numbers 2, 5, 8 are always with the orange numbers, aren't they? And I also know that the orange numbers 1, 4, 7 always are in the sets of the green numbers. Oh, I've done the wrong thing, you silly boy. That should be 1, 4, 7. I notice there's some kind of overlap with this kind of thing. I notice that whenever I've got 1, 4, or 7, it has to be 2, 5, 8. So if I've got 1, 4, and 7, there has to correspond to 2, 5, and 8. And then the other numbers, 0, 3, 6, 9, are kind of just behaving by themselves. That's interesting. So I could have a 1 to 2, a 1 to 5, 1 to 8, or a 4 to 2, 4 to 5, 4 to 8, or a 7 to 8, 7 to 5, 7 to 2, like so. So that's those kind of numbers, and this will produce 3 pairs. And then I have to get the remaining 2 pairs from this 0, 3, 6, 9 business over here. And if I put arrowed orders, I can have 3 to 0, meaning 30, 9 to 0, which is 90, and 6 to 0, like that. But I could have a two-way thing between 3 and 9, a two-way thing between 6 and 9, and a two-way thing between 3 and 6. Okay. So, what's going to happen here? Well, arbitrarily, I could just consider the combinations that involve these numbers up here. In actual fact, this thing here is called a bipartite graph. And what that means is you've got one set of numbers up here and they match to another set of numbers over here. We're going to do this in decision match, actually. We're going to do matchings. Oh, we're not. That's a shame. Okay, we might do matchings at some point then. It was in the old specification, and there's an algorithm for matching. It's like the alternate matching algorithm or something like that, where you go along and then undo one, then go along, undo one. You're working backwards and forwards as you trace along. But the point is, because every single element on the left or above, every single element here is connected to every single element down there, there isn't a unique or an optimal matching here. So we're free, essentially. So if I include, let's say I pick the first choice, or rather, let's do this more formally. Let's say there's the group G, which contains the set of numbers 1, 4, 7. And then there's another group H, which contains the set of numbers 2, 5, 8. And so if we consider G1, the first element, or just any first pick, or let's say GX is the xth position pick, then what we've got is, like, for G1, when we're picking the first element, then essentially we've got 6 combinations. Why is that? Well, let's say I started off with 1. I could have 12, 1, 2, or 15, 1, 5, or 18, 1, 8, and then I could have the flip of those, i.e. 21, 51, 81. So it's clearly going to be 6 combinations. If I then look at the second pick, I don't know, then I've only got 2 more numbers that they can match to, so that's only going to give 4 combinations. And then if I look at G3, there's only 2 combinations left because all the other numbers have been combined. So really, that's a total of 6 times 4 times 2, which is 8 times 6, which is 48 combinations. So just by looking at this configuration up here, with 147 mapping to 2, 5 and 8, they can be matched. There's only 48 combinations going on over here. And now we've got to multiply that by the amount of combinations going on over here. So, what have we got? Well, if they involve 0, let's make that clear, there's only 3 combinations. They're listable, it's easy, it's either 30, 60 or 90. There's only 3 combinations. And then we multiply those combinations by the other 2. Well, in that case, there's only 2 combinations. That's because you've either got a 2-digit number which is AB, or you've got the other 2-digit number form of that which is BA. Whatever 2 is left, you can just switch between the 2, and it's fine, you're allowed to do that because you know the other 2 are not a 0. So in total on the right hand side you're only going to have 6 combinations there. So therefore the total combinations is going to be 48 times by 6, and 48 by 6, 6 8s are 48, 6 4s are 24, plus the 4 is 28, so that means there's going to be 288 combinations total. Okay. Yeah, so that would be my question 1. Okay, new sheet of paper, let's go question 2. Okay, for each positive integer, n is greater than or equal to 3. Let's do a different colour so it makes it a bit nicer. Let's have purple. For each positive integer where n is greater than or equal to 3, we define an n ring to be a circular arrangement of n, not necessarily different, positive integers, such that the product of every 3 neighbouring integers is n. Determine the number of integers n in the range of between 3 and 2018 inclusive of both of the bounds for which it's possible to form an n ring. Okay, so the product of the 3... Okay, fine. Right, so let's change this to a 2. Purple. Okay, so let's suppose when n is 3, an n ring. So when n is 3, what could we have? Well, we could have 1, 3 and 1, like that. And this works because from 3's perspective, 1 times 3 times by 1 would give 3. We want it to equal n. From this 1's perspective, if I times it by 1 and 3, that also equals to 3. And if I start with this one, 1 times 1 times 3 is also equal to 3. Okay, when n equals to 4, well, okay, we want things to multiply, right? And we're only allowed integers, so really it makes sense we can only use the integers 1, 2 and 4 in some way. Well, if I'm going to use the 2's, for example, I need a 2 there, a 2 there, and a 1 here. And now there's no such number from 1, 2 and 4 that will make that work. Similarly, if I had 2, 1, 1, 2, that wouldn't work, because if I looked at the 2's perspective, then 2 times 1 times 1 is just 2, so that's not going to work either. The 2's have to be next to each other. In actual fact, I didn't need to consider that case because I needed to make at least one pairing of 3 correct. And then for the 4, so let's say I have 1, 4, 1, 1 like so, then there's no such number that we'll put here for this to work either. For example, 1 times 4 is 4, so that has to be a 1 by this combination. But then if I look at this combination of 3 neighbouring ones, 1 times 1 times 1 equals 1, so that's not going to work. So I think that's pretty exhaustive, n equals 4. Let's do a couple actually. N equals 5. Well, again, that's prime, so that's going to be dumb. It's 1 and 5. So, I mean, it's going to have to be the case of 5, 1, 1, but now we've got 2 elements to go here because we want a circle of 5 elements. From this 1's perspective, this would have to be a 1. But then from this 1's perspective, this would have to be a 1. And then we've got this 3 multiplying to 1 and this 3 equaling to 1. So that's not going to work. So there's no such numbers in the set of 1 to 5 for which this is going to work. Now n equals 6. We've actually got more to play with. 1, 2, 3 and 6. Well, what can we have here? Well, we could have 1, 2 and 3, right? And now we have to think of 3 digits that go here and here and here that satisfy this. Is this possible? Well, if I consider from this 3 times 2 is 6, so that means this number here is 1. And now if I consider from the 1's perspective, 1 times 2 is 2, so that must make this digit here a 3. And now, if I consider from this perspective, then 3 times 1 times the green thing must equal 6, so this must equal 2. And now this has actually satisfied it. This is an n ring. Is it unique though? Maybe we're not necessarily being asked about finding unique n rings. Was it n unique n rings? What did it say? For each positive integer, we define an n ring to be a circular arrangement of n, not necessarily different positive integers, such that the product of every 3 determine the number of integers n. So we don't care. I mean, as long as we can find it for that n value, we don't care how many there are. Okay, interesting. Is it possible though to do multiple ones? Because I feel there's multiple factors here, and maybe finding another one will give us a clue. So what's another way of getting to 6? Well, we could have had 6, 1, 1, right? Well, if I start from this 1's perspective, 6 times 1 times what is 6? This must be a 1 here. And then by symmetry, this must be a 1. And then that means that's a 6 as well. So in actual fact, n rings don't seem to be unique. So this is interesting. And already, I mean, it's difficult to say. We haven't really done enough to get some kind of pattern. Although 3 and 6 do tend to be a multiple of 3. And I think it's because we've got this every 3 neighbouring integers business going on. We may have multiples of 3. So let's suppose we're dealing with the ring n equals to n. So the general thing. So let's suppose we start at the top. Here's A1, and then A2, and then A3, and then we go all the way around, and the penultimate one is going to be AN before it loops back around. Now you've got this looping idea. And now we want 3 neighbouring things, neighbouring integers to multiply to n. So we've got A1, A2, A3 equals to n. We've got A2, A3, A4 equals to n. We've got A3, A4, A5 equals to n, and so on. And then the last couple of ones are going to be an minus 1 times by an times by a1. And then it's going to be an times by a1 times a2 equals to n. And then we're done. And then it's just going to loop back around in terms of all the triples that we could have considered. Now, I'm pretty sure, actually, that just by dividing, look, I've got A2 times A3 there, I've got A2 times A3 there. So since n does not equal to 0, and A1 up to AN can't equal to 0 either, we're just going to get that if I divide one by the other, I'm going to get, let's say, A1 over A4 equals n over n, which is 1, which means A1 equals to A4. And then I could pull the same trick later on. A3 and A4 is there, A3 and A4 is there. I divide this row by this row, then I have A2 over A5 equals n over n, which is 1, and that will get A2 equals to A5. Now what's going on is this 1 to 4 is going up in 3, so then that's A7, and then the next one will be A10, and the next one will be A13, and so on and so on. So what we've got, and then this one is going to go A8, and then this one is going to go A11, and so on and so on. And then the other strand, it's very similar to the first question actually, in terms of multiples of 3. You're going to have A3, then A6, and A9, and so on and so on. So really, we've got two types of numbers. We've got A3n, we've got A3n plus 2 maybe, and this is A3n plus 1. Now, here's the deal. There's going to be two types of things that happen, isn't there? Because there's two outcomes. I cannot spell outcomes. There's two outcomes. Either n is divisible by 3 or not. In the case of divisible by 3, then is this yes an n ring? Is this possible to have an n ring? And is that what they defined n rings to be, or are we just saying n ring? Yeah, okay. Why is it possible? Because we only need 3 factors of n for this to work. I.e., we could have the trivial case of 1, n, and 1, and repeat every 3 terms. For example, let's say we've got n equals 12. Well, there'll be 12 terms, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I'm saying that a really trivial way of solving this is just using the numbers 1, 12, 1 over and over again in blocks of 3, and this will work. So 1, 12, 1, 1, 12, 1, 1, 12, 1, 1, 12, 1. And now if I look at all the 3's, so that, and then this group of 3, and then let's say this group of 3, and then another group of 3, they're all going to work. Let's choose a different group of 3. So that's 1 times 12 works, and then we've got the 1 times 12 times 1 works, etc. It's always going to work because there's always A3n's, A3n plus 1's, and then A3n plus 2's cycle of 3. There's always going to be that cycle. So if n is divisible by 3, that's totally fine. So from 3 to 2018, there are, well, if we do 2018 divided by 3, 3's into 20 goes 6, remainder 2, 3's into 21 goes 7, 3's into 8 go 2, remainder 2. So that means 2016. So that means there's 672 combinations, or rather 672 cases rather, just from that. So when n is divisible by 3, there's 672 cases. Now, when n doesn't divide by 3, then that means, well, what's going to happen? You'd have A1, A4, A7, and so on, up to, this would be 3n plus 1. But because n doesn't divide by 3, then what would happen? It would loop back round, but it wouldn't start at 1 this time. It would start at either A2 or A3, depending if it was the form 3n plus 1 or 3n plus 2. As this A, sorry. Right, if it was 3n plus 1, so what would happen? So it would either go for A2 and then A5 and so on. Then you add another 3 and it will eventually end up at A of 3n plus 2, or it would be A3, A6, A9 and so on, and that would end up at A3n. And then in this case it would loop back to here, and for the 3n plus 2 case, what would happen? Well, let's think about it. If n was 1, then so suppose if n was 1, this would be 3 lots of 1, which is 3 plus 1, so that's A4. So there's 4 terms. Maybe I shouldn't have used n. Let's use k instead. Let's use k, this is k, this is k. Have I used it elsewhere? Yeah, I have. Let's call this k. Let's not confuse ourselves because there's already an n in the question. Then if k equals 1, then that means n is 4. So if we started on that, what would happen? It would go 1, and then it would go A1, and then we go 3 ahead, it would go to A4. And then if we went to 3 ahead, it would go 1, 2, 3. It would then go to A3, which is the 3k plus 2 term. But if we were here, k1, so actually this is going to be 3 lots of k, this is n is 5. It's going to loop round. The point is, it's not going to be a perfect loop. It's just going to it's going to cycle the whole thing. So what's going to happen is, if n doesn't divide by 3, if n doesn't divide by 3, then A3n equals A3k equals A3k plus 1 equals A3k plus 2 for all k, i.e. all the elements are going to be the same. So that means this will only be an n ring if and only if n is a cube number. So we now have to think of all the cubes between between 3 and 2018. Well, so okay, let's write our n. And let's have our n cubed. Let's create a little table, nice and short. When n is 2, that's 8, 3 is 27, 4 is 64, 5 is 125, 6 is 216, 7 is 343, 8 is 512, 9 is 729, 10 is 1,000. 11 is 1,331. 12, I want to say is 17 something. 144, which is 12 squared times 12. 2 times 8 is 2 times 4 is another 8. That's a 2, 4, 4, 1. 8, 2 is a 1, that's a 7. 1,728. And 13 squared is going to be 169 times 13. 3 9s are 27. 3 2s are 18, plus the 2 is 20. 2 is a 2. Oh, geez. No. Delete, that's a 5. 9, 6, 1. Well, this is clearly going to be 21 something. So that's too big. Next of all, I've already considered the case when n is divisible by 3. So I can't have the 12, the 9, the 6 and the 3. So I've only got 1, 2, 3, 4, 5, 6, 7. 7 new combinations here. So therefore it's going to be my 672 plus my 7 new ones. So therefore the total n rings is going to be 679. Okay. So I'm pretty happy with that answer. Let's have a look at question 3. Okay, let's have a different colour. Let's go green. Aries multiplies 2 integers which differ by 9, and Grace multiplies 2 integers which differ by 6. They obtain the same product t. Determine all the possible values of t. Okay, fine. So let's tell you what. Let's go here. So let Aries, not areas. Let's say Aries numbers. Let's have them be x and x plus 6. Are they differing by 6? Or was that the other one? I'm getting confused. Okay. So Aries differs by 9, and Grace's differ by 6, and they product together. Okay. Okay. Right. So I've got Aries 9, Grace 6. Okay, so fine. So let's say Aries' 2 numbers are those, and Grace's 2 numbers are, let's say, y and y plus 6. And we're saying if we multiply these two things, that means x times x plus 9 is going to equal y times y plus 6. They can be integers. Did they say they're integers? That'd be nicer if they were. Yes, integers. Cool. So this is a Diophantine equation. This is nice, actually. This is going to drastically reduce the number of solutions it's going to have. So, okay. Well, let's expand these out. So I've got x squared plus 9x equals to y squared plus 6y. If I just want to get them down to a single x, maybe, and a single y, then let's have x plus 9 over 2 squared minus 81 over 4. So this is going to be completing the square. And on this side I've got y plus 3 squared minus the 9. To make this easier, let's make that 9 a minus 36 over 4. Oh, this is going to be a difference of squares, isn't it? Okay, cool. So we'll take the y plus 3 squared to the other side. So I have x plus 9 over 2 squared minus the y plus 3 all squared. And then I'm going to have minus 36 over 4 plus 81 over 4. And 36 is 4 nines plus 9 nines is going to be 5 nines. So that's 45 over 4. Right. Okay, fine. Um, okay, if we times everything by 4, I'm going to get 4 lots of x plus 9 over 2 squared minus 4 lots of y plus 3 squared equals to 45. The reason I've done that is because this is a Diophantine equation, so we're wanting integer answers, and it would be nice to just get rid of the fractions. So I noticed that 4 is 2 squared, so I can take 2 as a factor inside of this, so it's actually going to be... yeah, so if I take this, this is like the binomial expansion. We can put it back into the binomial. So we're actually going to have 2 times x is 2x plus 9 minus 2y plus 6. Okay. Oh, these are all squares, aren't they? Right. So, I notice a couple of things actually. 2x plus 9 is what happens when you sum these two together, and 2y plus 6 is what happens when you sum these two together. So let's call the sum capital X equals 2x plus 9, and let's call capital Y 2y plus 6. And now we're going to be asked to solve capital X squared minus y squared equals 45, bearing in mind that these are integers, and clearly 45 is an integer, and then x squared minus y squared is just x minus y times by x plus y equals 45. Couple of things. Oh, could they have been different? Okay, fine. Now 45, this is an integer as well, because it's an integer minus an integer. This is an integer because it's an integer minus an integer. And so to narrow this down, we just have to think of all the integer pairs that make 45. So I could have, I could have 1, 45, I could have 3 and 15, and I can have 9 and 5, can't I? Don't think there's any other ways of doing it. Okay, so let's consider the case when we've got x minus y equals 1 and x plus y equals 2. The larger one, which is 45. Clearly, if I add the two together, I'm going to get 2x is 46, so x is 23. And if x is 23, y is going to be 22. So that's one potential set of solutions. And I can work backwards to work out what the two numbers were. Because clearly capital X is 2x plus 9. Yeah, I can work, that's fine. As long as I can get capital X, capital Y, that's totally fine. And then let's try another one. Let's try x minus y. Did these numbers have to be positive? Getting ahead of myself. No. Aries multiplies two integers which differ by 9. Ooh, they could be negative. Okay. Right, fine. If we tried it the other way around, let's say x minus y equals to 45 and x plus y equals to 1, then if we added these two things together, I would still get x equals to 23 this time. This time, 23 minus what is 45? Y would be negative 22. So is that true? If I just flip the orders, only the y is going to change sign? Well, let's try it for the other two. So let's consider the case. So this was the case of 1 times 45. And this was the case of 45 times 1. Let's consider the case of 3 times 15. So x minus y is the smaller one, which is 3, and x plus y equals to 45. If I add the two together, that's going to be 2x equals, not 45, you silly boy, it's 15. If If I add the two together, 2x equals 18, so capital X equals 9. And then y is going to equal 6. Is it the case if I flip these round, i.e. x minus y equals the 15 and x plus y equals the 3, is it true that x is 9 and y equals negative 6? Yeah, does appear to be the case. Okay. And then we've got the 9 and 5. So x minus y, well, let's do it. I don't know why I did this. I should have done them in ascending. That's 5 and that's 9. So let's try the case of 5 and 9. This is the case of 15 by 3. So if x minus y is 5 and x plus y equals 9, if I add the two together, it looks like 2x is 14, so x is 7. So y is going to be 2. So does that mean x is 7 and y is negative 2 for the other way around? X minus y is 9 and x plus y equals 5. I believe that's the case. So what am I saying? This is the 9 by 5. Okay, so it looks like determine all the possible values of t. Well, it looks like there's 6 contenders here. The problem is some of them might be copies of each other. For example, this one might end up to be this one, or this one might be end up to this one, and so on. So at most, there's 6 solutions here. So let's just give that a crack then. So remember, capital X was 2x plus 9, wasn't it? Yes, it was. So if 2x plus 9 equals to 23, then that means 2x is 23 minus 9, which is 14, so x is 7. So maybe I should draw a little table of x's and y's. Oh man, I'm such a mong. So this is x and that's the y. So in the case when x was 7, I don't need to draw a table, there's only 6 of them. It's going to be easy. So when x is 7, then what was y? Well, y was 2y plus 6, wasn't it? 2 little y plus 6, and that equaled to... Mate, why is my iPad being silly? That equals to 22. 22 minus 6 is also 14, isn't it? No, oh dear me, it's 16. So then 2y is 16, so y equals 8. So let me just check that that's true. So 7 times by, and then 9 add 7 is 16. Is that the same as 8 times by, and then 6 add 8 is 14? Is that necessarily true? Well, yeah, I mean, if I divide 14 by 2 and times this by 2, yeah, no, that works. Okay, so t in the case of 7 times 16, which is 7 times 8, which is 56. 56 times 2 is 112. So I'll hang on to that. So t could be 112. Does much change when capital Y is negative? Well, okay, so when capital X is 23, that means little x is 7. And when capital Y is negative 22, then 2y plus 6 is 22. Oh man, is that true? So if well no, they're going to be the same, aren't they? Because if this x is the same, it's just going to be 7 times 16 again. I'm just going to get a different way of multiplying to t equals 112. Just to check this is right, minus 22 minus 6 is going to be minus 28. So 2y is minus 28, so y is minus 14. So then the combination there is going to be minus 14 times by a number that's 6 on from that, which is minus 8. And that's just the negatives of these things, so yeah, that works. So I've got a sneaky suspicion actually that these are all going to be various values of t. Okay, so actually, let's just do. Okay, so if capital X equals 9, which means 2x plus 9 equals to 9, then it looks like 2x equals to 0, so x just equals 0. So that means the t value is just going to be 0. Oh, that should have been an easy one. T is 0. Yeah, because they both could have picked 0 and then 6 on from 0, 9 on from 0, i.e. there's one trivial solution, 0 times 6 equals 0 times 9. This is Grace's, this is Aries. Yeah, of course t is 0 should have been a solution. That's almost a trivial one, but that's good. So if we go back to it, this is the case when t is 112. This is the case when t is 0. I wonder what the bottom one's going to be. Well, that's when capital X is 7. So capital X is 7, so that's 2x plus 9 equals 7. Minus 9 from both sides is minus 2. So 2x equals minus 2, so x equals to minus 1. So that means we're going to have minus 1 times by 9 on from that is 8. So that means t is going to be negative 8. Yeah, so t is 8 there. So actually, what was the question it wanted for? Determine all the possible values of t. Well, there you go. So the three possible values of t. So therefore, t can equal minus 8, 0, and the last one was what? 112? There you go. Just those three. Cool. All right. Let's have a look at question 4. Okay. Have we had orange before? No, we haven't had orange. Right. Let gamma be a semicircle with diameter AB. Okay, so let's do that. So here's my question 4. Semicircle AB. Now, my tools can't draw semicircles, so I'm just going to have to leave it like that. And so I'm only interested in A and B over here. So for all intents and purposes, this thing over here is my semicircle. Okay. The point C lies on the diameter AB and meets E and D. And points E and D lie on the surface of arc BA. The point C lies on the diameter AB. Okay, fine. So there's a point C somewhere on here. Let's put it there. So it's not on the origin, on the centre. And the points E and D lie on the arc B to A. Okay, so E and D. So I don't know, let's have maybe E over here. That's a terrible E. Let's have E there, and let's say, just so it's completely not symmetric and we've got a general thing. In actual fact, that E's directly over C. So maybe I'll put the C there and maybe an E over here. And then let's say D like that, for example. Okay. Let the tangents to gamma at D and E meet to F. So I need to draw tangents. So that tangent's going to go like that, say. Mate. So I've got a tangent looking like this, maybe. E, and I've got a tangent of D. Looking like that, say. That's terribly drawn, but this point here we're saying was F, wasn't it? Tangents, let the tangents of gamma at D and E meet to F, and suppose that the angle ACD is ECB. Okay, ACD and ECB. Okay, ACD. So that's going to be, mate, come on. Never wants to behave itself. Okay, ACD, so this is X. So angle ACD. And then it was ECB, wasn't it? So let's call this X as well. That equals to angle ECB. Okay. Prove that EFD is ACD plus ECB. Okay, so these previous ones, so essentially we want to show this is 2x, because x plus x is 2x. So where is EFD? Okay, so we need to find this one up here, we'll call y. Okay. Right. Right, how are you going to do this? Well, what angles do we know? Well, we know this angle here is 180 degrees minus 2x. What else can we do? Well, I can draw a vertical down there like that maybe, and a vertical down there like that. So this is 90, this is 90, and then this thing here is 90 minus x. And this also is 90 minus x. I think we can. Yeah, okay, let's get rid of this green thing. If I carry that on, so it's now a reflection, this is also x, this will be 90 minus x, and then if I carry this down, make that like that, so that's reflected as well, that's a 90, this will also be x, and this will be 90 minus x. I don't know, let's call this G and let's call this H. Then clearly, because I've got 2x here and 2x here, because of vertically opposite angles, so because of vertically opposite angles, ECG is a straight line, and DCH is also a straight line. Okay. Why is that useful? Alternate angles, isn't it? Yeah, so really I need to work out these angles here. So I know what this bottom one here is at C, which is 180 minus 2x. And then this angle here, if I was to spin this around, what does that correspond to? Oh, I feel I've got this somehow. Can I work out what that is? I can't seem to. I mean, if I draw a line from there to there to make this one big triangle, I don't know what these two angles are, so it's not going to be useful. I think what I can do though is if I draw a line from here to here, like that, I can work out what this angle is, because if I consider this big triangle here, then by the alternate segment theorem it must be 90 minus x. So this must be 90 minus x. So, okay, we need to do that then. So because by the alternate segment theorem, angle FDE is the same as angle DGE, which equals 90 degrees minus x. And then I think I can do a similar thing over here actually, because by the alternate segment theorem of this thing, let's not use orange, I've used orange already. If I consider this angle here, then by this triangle, then it should equal this down here, which is also 90 minus x. So actually, by the exact same thing, the exact same argument, like this, so make it purple, FED this time, FED would equal DHE. And this is 90 minus x. And then we have sum of angles in a triangle equals 180 degrees. Therefore, for triangle, what is it, D? So for triangle DFE, we have 90 minus x plus 90 minus x plus y equals to 180 degrees. So the 90 and the 90 and the 180 will cancel if I minus 180 from both sides. So I have y minus 2x equals to 0. So y equals 2x, and that necessarily proves that the angle, what is it, DFE? Proves the angle DFE equals the angle DCA. No, how did they word it? ACD ECB. So ACD plus angle BCE, was it? But how have I not memorised this? ECB, damn it. ECB. Almost there. ECB. I think that's all the proof you need, surely, and a good diagram. I think you just had to draw a straight line down. There's probably other ways of doing it. I mean, this seems like a fairly straightforward circle theorems problem. I'd say it's pretty easy for a British Mathematical Olympiad question, in all fairness. I'm just a bit spooked out that yeah, maybe I could have formalised and written what was going on here, but you know what, I could just consider the following diagram where, and then, you know, that. I think that's fine. I don't see the problem with that. No, just a bit spooked out. It seemed like a really easy question. Right. Okay. Right. What colour have I not chosen? Pink. Have I used pink before? Okay. Two solid cylinders are mathematically similar. Okay. The sum of their heights is 1. Okay, so the sum of their heights is 1. The sum of their surface areas is 8 pi, and the sum of their volumes is 2 pi. Find all the possible dimensions for each cylinder. Okay, right, so they're similar. So we've got something like this. Right, so what was this, question 5? How are we doing for time? Oh, geez, just over an hour, got loads of time. Okay, right, so we've got a cylinder. Oh mate, come on. We've got a cylinder looking something like that maybe. And this has got some radius r, and it's got some height h. And now I want a similar thing to this. Where it's shrunk down, or it's whatever. Now this is h prime and r prime, and all we know is that h plus h prime equals to 1. Yeah, is that what it's... Oh no, I didn't copy the thing. Oh man, did I write all that stuff? And oh, I'm such a mongrel. Right, so just to recap, it was the sum of the heights was 1, the sum of the areas was 8 pi, and the sum of the volumes was 2 pi. I think that's what it was. Let me just double check. So 1, 8 pi, 2 pi. So 1, 8 pi, 2 pi. Yes, okay. Right. Well, my immediate concern is I've got 4 variables here: r dashed, h dashed, r, and h dashed. Not good. And I don't want to have to deal with it, because although I've got a relationship between h and h dashed, I don't have a relationship between r and r dashed in the same way. But what I do know is they are mathematically similar. So let's suppose, I don't know, let's call the scale factor alpha. So alpha is the scale factor. Right, so let's just crack on and do what we're supposed to do. So factorising as we go along is probably going to be the best thing forward. So in terms of the heights, we've got h1 plus alpha h, so 1 plus alpha, equals to 1. Okay, that's equation 1. And now surface area, I mean, you can probably just do this straight away. It's 2 pi r times by r plus h. Right, if you think about it. Because you can have 2 pi r times r, which is the 2 circular bits, and you have 2 pi r times by h, which is going to be the kind of like the label of the baked bean can, if you like. So that's going to be total surface area. And now remember, when you've got length, area, and volume scale factors, that if the length scale factor is alpha, the area scale factor is alpha squared, and the volume scale factor is alpha cubed. Just from year 9, year 8 stuff from earlier on in school. So we're immediately going to get 2 pi r times by r plus h times by 1 for the larger one, and then alpha squared, because it's a surface area, equals 8 pi. And here, I'm guessing we're assuming that alpha is trapped between 1 and 0. If alpha was bigger than 1, it just means our original cylinder here is the smaller one. It doesn't particularly matter. Anyway, so if I notice that I can divide by 2 pi here to make things a bit easier. So 8 pi divided by 2 pi is 4. So I think that will do for the second equation. So this is for the lengths, this is for the areas. Now for the volumes. Well, the volume is just going to be pi r squared times by h. And then same deal, we're going to have 1 plus alpha cubed. 1, because 1 times pi r squared is going to be the larger one, and alpha cubed times that is going to be the other one, or the smaller one. And this equals to, 2 pi. So if I divide by pi on both sides, then at least I have this to deal with. Okay, well, I have got, the good news is that I now have 3 equations with 3 unknowns. That is alpha, r, and h. So that means this can be potentially solvable. And because they're all factors of each other, or no, that's not true. Because they're all written in factorized form, then maybe we should try dividing, multiplying to eliminate variables. Okay, so I notice that the area one has got this r plus h term in the middle, so I'm probably going to save that till last, and the reason for that is because that's not a nice thing to deal with. However, if I look at the upside, the up to, so that one, I can clearly write that from L we're clearly going to have h equals 1 over 1 plus alpha. So that means if I substitute this in to the volume one, we're going to get r squared times by h, which is 1 over 1 plus alpha, and then that's times by 1 plus alpha cubed, and this equals to 2. Right. Fine. So what does that mean? Well, I mean, put it this way, 1 plus alpha cubed can be divided by 1 plus alpha. How do I know that? Because if I said let my function of alpha be 1 plus alpha cubed, and let's say a different function of alpha, let's say g of alpha, and that was 1 plus alpha, then if I was to set them both equal to 0, clearly alpha equaling to minus 1 would be a solution to both of them. So what this means is 1 plus alpha can be written as 1 plus alpha times by something, and 1 plus alpha cubed can be written as 1 plus alpha times by something else by the factor theorem. So clearly 1 plus alpha is a factor of 1 plus alpha cubed. I could probably work out what that is. It's going to be some quadratic thing. Do I need to know what that is? No, you know what? I'm just going to leave it because I don't want some ugly... No, I'm just going to leave it. I'm just going to totally leave it. So, let's now substitute this back in to the area. So I now know what... well, actually, I haven't quite finished with this one, have I? Got r squared as that, which leads to r equaling 2 times 1 plus alpha over 1 plus alpha cubed, and this is all square rooted. So now I've got expressions for r and h, which isn't actually too bad. So if I sub it into a, I've got r, which is the square root of 2 lots of 1 plus alpha over 1 plus alpha cubed, times by the same thing again, because it's r plus h, so this thing, plus h, which was 1 over 1 plus alpha, and then this is times by 1 plus alpha squared, and this equals to 4. Okay. To get this over... Right, so I've got to solve for alpha, right? Brilliant. Fine. So I'll tell you what, I'll write this as over the square root of 1 plus alpha, and then I'll have it squared. Why would I want to do that? Actually, I want it the other way around. I want it to be the square root of 1 plus alpha all squared like that. There you go. So let's think about this very carefully. When I do this term times by this term times by this term, I am just going to get 2 lots of 1 plus alpha times by 1 plus alpha squared all over 1 plus alpha cubed. And then when I do this term times by this term times by this term, I'm going to get some horrible, well, I'm going to have the square root of, and then on the top I'm going to have 2 lots of 1 plus alpha, and on the bottom I'm going to have 1 plus alpha cubed times by 1 plus alpha all squared, which means this can cancel with this, so I can move this along, and that's all times by 1 plus alpha all squared. So actually I can move that over here, and I can actually make that a 1 plus alpha squared all squared and put it in the surd, and this equals to 4. Okay. Right. So what can I do? Well, I could multiply everything by that. I think really it's the trick is going to be undoing this square root thing. So I'm going to get this term to the other side by subtracting it. So that goes over to there. And then this can bugger off. This can go here. That's not a problem. Oops, daisy. And then if I get the term on the right over a common denominator, I'm going to have 4 lots of 1 plus alpha cubed minus 2 lots of 1 plus alpha times by 1 plus alpha squared over here, all over 1 plus alpha cubed. Oh man, this is going to be nasty. This is going to be some... Well, I've already got cubed, so if I square both sides, I'm going to get some to the power 6. Oh dear. Right, okay, so I'm guessing this polynomial is going to factor out really nicely. Okay, so I'm going to get this stuff on the left-hand side still. And now if I square both sides, that disappears, and this just becomes a big fat square. Oh boy. Oh, do I even want to do this? Wow. Okay. No, this is fine. This is absolutely fine. Because... No, this is fine. Because I'm going to have 4 lots of 1 plus alpha cubed minus 2 lots of 1 plus alpha times by 1 plus alpha squared, and then this is all squared. And then this is going to be all over 1 plus alpha cubed squared. And this is going to equal 2. And if I get it over a common denominator, then I really do need to times this by 1 plus alpha. Do I? Do I really? No, I don't think I do. Hold on, let's back it up a little bit. Okay, over here, 2 lots of 1 plus alpha squared, and ideally I want this denominator to be 1 plus alpha cubed all squared. Now I've got the 1 plus alpha here. So really, actually, I'm going to need to know what I need to multiply. So 1 plus alpha times by what is going to give 1 plus alpha cubed, like that, so that I can whack it on the bottom. That would be better, because if I just multiply, yeah, I wanted to keep it as low as possible, so this is going to have to be times by something else. Right, well this has to be a 1, because 1 times 1. I'm going to need an alpha squared at the end, and I'm guessing this is going to be a minus alpha, because 1 times minus alpha is plus alpha, and then plus that's going to be fine. Then I have a minus alpha squared there, but a plus alpha squared. So actually, I need to times by 1 minus alpha plus alpha squared, top and bottom, so that works out. And the reason I've done that is because now I can subtract all of this to the other side. This feels more like a BMO question. Or maybe I'm just making a meal of it. This is a lot easier than it actually should be. Then I can take all this stuff to the other side, like that. So I bring this over like that, subtract this over like that. And then because this equals to 0, then only the numerator has to equal to 0. So actually I can get rid of these things. So now I've got a to the power 6 polynomial. Jesus. Okay, well let's just do it by parts, in bits. Okay. Oh man. Right, so the highest power we've got here is cubic. So I'm going to have a 4 cubic here, but then I'm going to have a minus 2 cubed there, so this is going to be a 2 alpha cubed. So that's all the cubes done. What else am I going to have? The squareds. There's no squareds there, but I'm going to get a minus 2 times 1 times alpha squared. So it's a minus 2 alpha squared here. In terms of alphas, I'm not going to get any from here, so I'm going to get minus 2 times alpha times 1. I think that's the only way that's going to come out, so it's minus 2 alpha. And then the constant terms, I'm going to have 4 times 1, which is 4, minus 2 times 1 times 1, which is minus 2. So that's just going to be a plus 2, isn't it? And then that's all squared. And then I've got minus 2 lots of, and let's do this in stages. 1 plus alpha squared is 1 plus 2 alpha squared plus alpha to the 4, and this is being times by 1 minus alpha plus alpha squared. Oh, geez. Right, okay. So let's dive in for this a little bit. I'm going to have a 1 times 1. Am I going to have any alphas? Yes, that's going to be this minus alpha times that, so it'll be minus alpha. Am I going to have any alpha squareds? Yes, because I'm going to have a 1 times this alpha squared, but then a 1 times this 2 alpha squared, so that's actually 3 alpha squared. So that will happen. Will I get any alpha cubes? Just this minus alpha times that, so it'll be minus 2 alpha cubed, won't it? I don't think there's any other combinations. Will I get an alpha to the 4? I'll have a 2 alpha to the 4 there, plus 1, so it's actually plus 3 alpha to the 4. Will I have any alpha to the 5? So I have this alpha to the 4 times this minus alpha. I think that's the only one, so it's going to be minus alpha to the 5. And will I have any alpha to the 6s? Yes, I'll have a plus alpha to the 6 there, won't I? Right. Okay, luckily this thing up above is a lot easier because there's 2's everywhere, so I can take the 2 out, so 2 squared, that makes that a 4. So I'm just going to have alpha cubed minus alpha squared minus alpha plus 1 all squared popping out of here. Mercy, mercy me. I hope this tidies up. I've made a mistake and there's some real problems. Okay, so 4 lots of. Right. If I square this, the only constant term is going to be the 1 times 1, so that's a 1. The alpha term, well, I'm going to have a minus alpha times 1, or the other way around, so that's minus 2 alpha. The alpha squared term is either going to be the minus alpha times minus alpha, which is plus 1, or the minus alpha times the 1, which is a minus 1 alpha squared, or the other way around, which is another minus 1, so that's actually minus alpha squared, I believe. For the cubed, I'm either going to have minus alpha times minus alpha squared one way around, which is plus 1, or the other way around, and the other way around, so it's going to be another plus 1, or I'm going to have an alpha cubed times 1, which is another plus 1, so I believe that's 3 alpha cubed. Right, alpha to the 4. Well, I'll either have minus alpha times alpha cubed, which is minus 1, or I'll have it the other way around, so that'll happen again, or I'll have the minus alpha squared times by itself, so it's plus 1, so they cancel, so that's just minus alpha to the 4. Will I get an alpha to the 5? I think that's only going to happen when it's that times that, or the other way around, so that's minus 2 alpha to the 5. Oh, and by symmetry, yeah, then this must be alpha to the 6. Yeah, that makes sense. 1 minus 2, 1 minus 2, minus 1, 3. Yeah, cool. That seems legit. Okay. Fine. Oh, and this horrible thing, and then I'm going to put them side by side underneath each other. So I'm going to whack that there. Like this. So what equals to 0? So I've got 4 times 1 minus 2 times 1 is just going to be 2. So that's the numbers done. 4 times minus 2 is minus 8. And then minus 2 times minus 1 is going to be plus 2. So I believe that's a minus 6 alpha. And then I've got 4 times minus 1, which is a minus 4. And then minus 2 times plus 3 is a minus 6. So that's going to be a minus 10 alpha squared. And then for the cubes, I've got 4 times 3 alpha cubed, so that's 12. And then minus 2 times minus 2 is going to be plus 4. So that's going to be plus 16 alpha cubed. I really hope this works out. And then 4 times, that's going to be a minus 4. And then minus 2 times 3 is going to be minus 6. It's going to be minus 10 alpha 4. Oh, I really hope there's some symmetry here, because I can see a minus 10 twice. And then I've got 4 times minus 2, which is going to be a minus 8. And then minus 2 times a minus 1 is going to be plus 2, so minus 8 plus 2 is minus 6. Oh, it is symmetry, yes! Oh, this is going to be nice, I can tell, because I'm going to do a substitution with this. Yeah, boy. 4 times 1 is 4, and then minus 2 times 1 is minus 2. 4 minus 2 is plus 2. This is to the 5, and this is alpha to the 6. Yeah, boy. Oh, home stretch. Home stretch. This is not nice. Okay, first of all, these are all even. So 0 equals 1 minus 3 alpha minus 5 alpha squared plus 8 alpha cubed minus 5 alpha to the 4 minus 3 alpha to the 5 plus alpha to the 6. Okay, first of all, this is symmetric. This is symmetric. And one of the ways of dealing with a polynomial that's symmetric like this is, I don't know, let x equal to alpha plus 1 over alpha. And I mean, the reason why I do this kind of stuff is because you see this in complex numbers actually a fair bit. trying to think what it is now. I think like if you've got 1 over z plus z, then this is some 2 cosine of something with complex numbers, and it tends to work out because, you know, if you've got z, which is cosine of theta plus I sine of theta, and then you've got z to the minus 1, which, you know, that's technically cosine of theta plus I sine of theta to the minus 1 when it's a complex number, so then that's going to be cosine of theta minus I sine of theta by de Moivre's, and then you add those two things together. Yeah, you see this in complex numbers all the time, and you actually use that argument to break down polynomials that are particularly large, using, is it de Moivre's theorem? Yeah, Euler's identity is de Moivre's theorem is when you bring the power down, so it's in the argument of the trig. Yeah, I always forget what it's called. But yeah, no, it's a thing. Okay, so you're probably thinking, okay, but I don't have any 1 over thetas there, so what we're actually going to do is we're going to divide, so we're actually going to divide by alpha cubed. And that's okay because alpha doesn't equal to 0, because then that means we, since there are 2 cylinders. I mean, if alpha was 0, then that means the scale factor is 0, so that means the second cylinder just vanishes off, is singular, it's nothing, it's just an infinitesimal point. It doesn't exist, we vaporized it. So dividing by something that's non-zero is perfectly fine. So we're going to have 0 equals alpha to the minus 3 alpha to the minus 2 minus 5 alpha to the minus 1 plus 8 minus 5 alpha minus 3 alpha squared plus alpha cubed. And then what we're going to do is we're going to tidy this up. So we've actually got alpha cubed plus 1 over alpha cubed. And then we've got minus 3 lots of alpha squared plus 1 over alpha squared. And then we've got minus 5 lots of alpha plus 1 over alpha. And then we've got plus 8 equals to 0. Now, be really careful here, because if x is alpha plus 1 over alpha, then what is x squared? Well, that's alpha plus 1 over alpha squared. And that's alpha squared, and then when you do alpha times 1 over alpha, that's plus 1, you can have 2 of them, so that's plus 2, and then that's plus 1 over alpha squared. So really, x squared minus 2 is alpha squared plus 1 over alpha squared. That's really important. So that means this thing I can replace with x with the substitution, this thing I can replace with x squared minus 2, and in actual fact, I'm going to pull this same trick. I don't know why I just didn't do this in red, actually. Let's do it in red. Style, red. This is a little thought bubble. Then what happens if I cube x? Well, then that's going to be alpha plus 1 over alpha cubed, which is alpha cubed, plus 3 lots of alpha squared divided by alpha, which is 3 alpha, plus 3 lots of alpha times by 1 over alpha squared, so that's 1 over alpha, and then plus 1 over alpha cubed. And I notice that this middle term here is 3 lots of alpha plus 1 over alpha, which is actually 3x. So I've got 3x plus alpha cubed plus 1 over alpha cubed equals to x cubed. So actually, this last term over here, funnily enough, can become x cubed minus 3x. And now actually, I think we're ready to roll, and we've now got a cubic. So we've actually got 0 equals x cubed minus 3x minus 3 lots of x squared minus 3 lots of minus 2 is plus 6 minus 5 lots of x plus 8. Yeah. So let's tidy this up. So I've got x cubed. What have we got? We've got minus 3x squared. So that's done, that's done. And then minus 8x. And then plus 14, is it? Equals to 0. Let me just check that. Have I made a mistake somewhere? Don't feel I have. Did I make a mistake earlier on? Let me just check. I think there's a problem here. I think it's the cubic one, isn't it? To get the cubic, I'd have that times that, and then that times that, so I'd have two of them. But I'd also have that times that, and that times that, so I'd have another 2, so it's 2 plus 2. So that's a 4, you silly boy. Okay, and if that's a 4, and I've got 4 times 4 is 16, and minus 2 times minus 2 is another 4, so 16 plus 4, so that's a 20. So when I divide by 2, that 8 becomes a 10. When I divide by all that stuff, that 8 becomes a 10. This 8 at the end becomes a 10. So I've got all this stuff. This becomes a 10. So it's not plus 14, that becomes a 16. Coolsies. Yeah. Yeah. Okay. How do we solve this though? Well, let's think about what 16 factorizes to. Well, 16 can either be its factors are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, or plus or minus 16. If I substitute 1 into this, I'll have 1 minus 3 minus 8 plus 16. This is minus 11 plus 16 plus 1 is, well, it's not 0, so it's not that. So x equals to minus 1 is not a factor because x equals to 1. If I substitute x is minus 1 into there, minus 1 cubed is minus 1. Minus 3 lots of minus 1 squared is minus 3. Minus 8 times minus 1 is plus 8. Plus 16, this is clearly not equal to 0. So that factor's gone. Let's try when x equals to 2. So this is the x minus 2 as a factor. 2 cubed is 8. Minus 3 lots of 2 squared. Well, 2 squared is 4, so it's minus 12. Minus 8 lots of 2 is 16. Plus 16. Yeah, that's not going to work. Although these cancel. The 8 minus 2. Okay, that's not going to work. What about when x is minus 2? Then we're going to have minus 8. Still minus 12. But now minus 8. Times by minus 2 is now plus 16. This is plus 16, so we've got 32 minus 20, so that's actually 12, so it's not going to work. What about when x equals to 4? Then we're going to have 64 minus 3 lots of 4 squared, so 3 16s are 48, minus 8 lots of 4 is 32, plus 16. Ooh, 64 and 16 is 80, and minus 48 minus 32 is minus 80. Yes, So that means x minus 4 is a factor. Okay, so I've got 0 equals, and then I've got x minus 4 as a factor. So then I have to have an x squared there. I have to have a minus 4 popping out there, because it has to be 16. And then I need a minus, this has to be a plus x, doesn't it? Because minus 4x squared gives me minus 4x squared, and then x times x gives a plus x squared, and this will result in a minus 3x squared, which we've got there. Then if I look at the x's, I've got minus 4 times this x and x times minus 4. Right, fine. So either x equals to 4 or x squared plus x minus 4 equals to 0, which I'm pretty sure if I complete the square on this, I'll get x plus a half squared. Oh man, really? Yeah, it's going to work, isn't it? And then minus a quarter, minus 4 is 17 quarters, equals to 0. So that means x plus a half equals to plus or minus the square root of 17 over 2. So then x is going to equal, minus 1 plus or minus the square root of 17 over 2. Right. So, oh boy. So x was alpha plus 1 over alpha. Where's my original substitution? Okay. Okay, so, right. So that means either alpha plus 1 over alpha equals to 4, or alpha plus 1 over alpha equals minus 1 plus or minus the square root of 17 over 2, not 12. Why did I put 12? Yeah, one of them is going to be a lot easier to solve than the others. So if I multiply by alpha both sides, alpha squared plus 1 equals to 4 alpha. So an alpha squared minus 4 alpha plus 1 equals to 0, which means alpha minus 2 all squared minus 4 plus 1 is minus 3. So then that means root 3 plus or minus root 3 add 2 equals to alpha. Oh man. Okay, and in that case, h was, what was h again? H was 1 over 1 plus alpha. So h was 1 over 1 plus this, which is 3 plus or minus root 3. And r was, wow, that thing. Hold on, you know what, I'm just going to copy these down. Well, I've got loads of time. To be fair, this was a mountain. We're going to climb it. So let's remember that's that. Let's whack that over there, say. So I'll put this over to here, and I'll put it that like that. Get rid of this, and I'll say, remember that dot dot underlined, and then we like that. Okay. So h could be 1 over 3 plus or minus root 3. Fine. And r could be the square root of, oh man, 2 times by 1 plus alpha, so that's 3 plus or minus root 3, all over 1 plus alpha, which is 2 plus or minus root 3, cubed. Yeah. So in either of those cases, so one possible set of dimensions is that h equals 1 over 3 plus root 3, and the corresponding r value is the square root of 2 lots of 3 plus root 3 over 1 plus 2 plus root 3 cubed. If you wanted to look at it that way. And then the other value was h was 1 over 3 minus root 3, which is positive because root 3 is less than 3. And the r value for that would be 2 lots of 3 minus root 3 all over 1 plus 2 minus root 3 squared. Root 3 is smaller than 2, so that's fine. Cool. So there's two potential values it could be. Maybe that stuff cancels down. We'll check it in a moment. I really need to get my head around this thing. Oh, is there a nicer way of doing this? I have no idea. Okay, fine. So if I take this, wow, this is not nice at all. So I multiply by alpha, I'm going to get alpha squared plus 1 equals this thing, which, you know what, for all intents and purposes, I'm just going to call this capital A. You know what, super lazy. So an alpha squared minus a alpha plus 1 equals to 0. So this root is going to be alpha minus a over 2 squared minus, and then this is going to be alpha squared plus 4 all over 4 equals 0. So that really should be a minus if I put this in a bracket, and then when I add that over, it's going to be a squared minus 4 over 4 square rooted, so that becomes 2, and then I'm going to add a, and there's plus or minus this thing, and this equals to alpha. So I know what a is. A equals -1 plus or minus root 17 over 2. I now really need to know what a squared is. Well, I know that's going to be a quarter, and it's just going to be -1 plus or minus root 17 squared. So 1/4 of -1 squared is always going to be 1. Positive or negative root 17 squared is always going to be plus 17. And then it depends. If I've got -1 times by positive root 17, there's 2 of that, then there's going to be -2 root 17. But then if it was negative times negative, that would be a plus. So actually, I'm always going to have 1 plus 17, which is 18, minus plus, depending on the plus minus up there, 2 root 17, and this is all over 4. So actually, I can cancel this down and make this a 9 and a 1. And this is all over 2. So actually a squared is always that. A squared minus 4 is always going to be 9 over 2 minus 4, which is 8 over 2. So that's actually going to be 1 minus plus root 17 over 2. That's good, actually, because 1 minus root 17 is negative, and you can't square root a negative number, so that means we have to have the plus, which means we have to have had the minus up here, right? Okay. So what does that mean? It means yeah, it means, okay, so that means alpha is going to be a where it's negative, which is -1 minus root 17 over 2, plus or minus, and then this is going to be the square root of 1 plus root 17 all over 2, and then this whole thing is divided by 2. If I times top and bottom by 2, then this becomes a 4 and this becomes a 2. was this again? Oh, I just rubbed it out. So that goes I can take this 2 and square it and put it inside. So that'll be a 4. That'll be a 4. This will be a 2. This can go and this can go. And this can go. Right. So alpha, to tidy this up, is going to be -1 minus root 17 plus or minus the square root of 4 plus 2 root 17, and this is all over 4. Wow. Is this even positive? Because alpha is the alpha's the scale factor, isn't it? So this might not even be a positive thing. Well, alpha cannot equal the negative of that. So alpha cannot be -1 minus root 17 minus the square root of 4 plus 2 root 17, whoops, not that far, all over 4, because then that would imply that alpha is negative, and I don't want any negative scale factors. That's just weird when we're talking about real space. So really, for this thing to make sense, we need that 1 plus root 17 is actually smaller than the square root of 4 plus 2 root 17. Is that even the case? Because we need this top thing to be positive, so we can add that thing to the other side. Yeah. Okay. Well, they're both bigger than 1. So it should make sense that if I square both sides, that should still hold. If I square the right-hand side, that's 4 plus 2 root 17. If I square the left-hand side, I'm going to have 1 squared, which is 1, plus root 17 squared, which is 17, plus 1, I'm going to have 2 root 17 there. So actually, I'll have 18 plus 2 root 17 there. So yeah, actually, if I minus that from both sides, this is clearly false. So actually, this doesn't seem to be making sense. As in, alpha, there's no real solutions for this. It doesn't seem, because it would mean that alpha, because then alpha cannot be negative. So it looks like the only solutions we're going to have are these ones up here, and I'm just curious as to whether they can be tidied up a little bit. For example, let's take these actually, because I get the feeling things are going to simplify. So the only two solutions, so only solutions that are feasible are these two. And now if I consider when h is 1 over 3 plus root 3, then if I rationalise that denominator, so by timesing by 3 minus root 3 top and bottom, then I have 3 minus root 3 on the top, and I have 3 times 3, which is 9, minus root 3 times root 3, which is 3, so I'm going to have that over 6. So I could have h equals 3 minus root 3 over 6, which is perfectly fine. And then the corresponding r to go with that, well, what would that r be? Well, that r was 2 plus 3 root, it's the square root of two lots of 3 plus root 3. This is all over. And then 2 plus root 3 all cubed. Well, I've got 1 plus. And let's think about this very carefully. I'm going to have 2 cubed, which is 8. And at the other end, I'm going to have root 3 cubed, which is 3 root 3. And then I'm going to have 3 lots of 2 squared, which is 4, times by root 3. So 3 times 4 is 12, so I'm going to have 12 root 3. And then I'm going to have 3 lots of, just because of the whole 3 choose 2 thing, 3 lots of 2 times by root 3 squared, which is 3. So I'm going to have 9 times 2, so it's going to be 18. So in actual fact, this is going to become R lots of 2 lots of 3 plus root 3 all over. And then this is going to tidy up quite a fair bit, isn't it? Because I've got 1 plus 8, which is 27, plus 12 plus 3 root 3, which is 15 root 3, and 27 and 15 root 3 have got a common factor of 3, don't they? So this is going to be 3 lots of 9 plus 5 root 3. This is all under 2 lots of 3 plus root 3. I'm just wondering if this cancels down anymore. I mean, this isn't wrong, but I just feel there's a better way of doing this. If I want to look back at the original equations, I mean, I know what this thing is. I mean, R is also the square root of 2, and then this will be over 1 minus alpha plus alpha squared. And I'm just wondering if that would just be an easier thing to deal with. So if I bring this down, where is it? Here. I can get rid of all this maybe. And what was this for the value of? This was alpha was 2 plus or minus root 3, was it? I think that's what it was, wasn't it? Yeah, alpha was 2 plus or minus root 3. Remember that I've got to be careful. H was 1 over 1 plus alpha, wasn't it? So this top one is when alpha is 2 plus root 3. And this bottom one is when alpha is 2 minus root 3. Yeah, okay. Cool. And R is the square root of 2 over 1 minus alpha plus alpha squared. So H can be written as this, and R can be written as the square root of 2 over 1 minus alpha, which is 2 plus root 3, plus alpha squared. Well, 2 plus root 3 squared is 2 squared, which is 4, plus root 3 squared, which is 3, so that's a 7, plus 2 lots of 2 plus root 3, 2 times root 3, so that's 4 root 3. The reason I've written it this way is because I can rationalise this denominator, and then hopefully it will be something a bit nicer. So this will be 2 over, and then 1 minus 2 is minus 1, but plus 7 is 6. And then minus root 3 plus 4 root 3 is plus 3 root 3. And then I want to times this by 6 minus root 3 top and bottom to give R equals the square root of 3 root 3 top and bottom. So I've got 2 times 6, which is 12, minus 6 root 3 on the top. And then 6 squared is 36, minus 3 root 3 squared, I believe, is 27. Yeah, so then that's going to be a 9. So this is actually going to be 1/3 of the square root of 12 minus 6 root 3. Which is fine, but I think I can tidy that up even more, because let's think of 12 minus 6 root 3 as potentially some a plus b root 3, where a and b are integers. Then if I square both sides, this is 12 minus 6 root 3, and then this is going to be a squared plus 2ab root 3 plus b squared times root 3 squared, which is 3b squared. Comparing coefficients, we're going to have a squared plus 3b squared equals to 12. And we're going to have 2ab equals to minus 6, which means ab equals to minus 3, which means a equals minus 3 over b. If I then substitute that into the quadratic thing, see if there's any integer solutions, then this is going to be 9 over b squared plus 3b squared equals to 12. I can divide everything by 3 to make this 3b squared plus b squared equals to 4, times by b squared everywhere to get 3 plus b to the 4 equals 4b squared, which means I've got b to the 4 minus 4b squared plus 3 equals to 0, which means I've got b to the 4, and this is a quadratic in b to the 4, so this is b squared minus 1 times by b squared minus 3 equals to 0, which means b equals plus or minus root 3, which we can't have because we wanted a and b to be integers, remember, or b equals plus or minus 1, which is fine because 1's an integer, and since a is minus 3 divided by b, then a is going to be minus or plus 3, because if it was positive 1, then a is minus 3 divided by positive 1, and if a was negative 1, then minus 3 divided by negative, okay. So that means I can write r as a, which is minus plus 3, and then b, which is plus or minus 1, lots of root 3, and then this is all over 3. Now the problem with this is minus 3 plus root 3 is negative, so that means we can't actually have these top solutions here, so it must be 3 minus root 3 being the thing in this case. So we've got actually that for a h value of 3 minus root 3 over 6, we've got also that r is 3 minus root 3 over 3. Now in the other case, if we have this, then what would have happened, rationalise that denominator, we'd have had to times by 3 plus root 3, top and bottom. So a similar argument, this would have been h is 3 plus root 3 over 6. And then what would have happened is all of this stuff here would have just had negative thingy bob, so this actually would have just cut to the chase. It'd be 3 plus root 3 over 3. So there's one solution, there's another. So we've actually got the 2 dimensions of the thing we're dealing with right there. So yeah, what did the question actually ask? I've forgotten now. 2 cylinders, blah, blah, blah. Find all possibilities for the dimensions of each cylinder. Well, there you go. The answers are there. And clearly, you know, by symmetry, one of them, I mean, I'm guessing actually that 3 minus root 3 over 6 times by either 2 plus root 3 or 2 minus root 3. It's probably 2 plus root 3. This is going to equal the other one, which is 3 plus root 3 over 6. Actually, no, it's probably more likely to be the negative one, isn't it? Well, hold on, what have I got? I've got 3 times 2, which is 6. I've got 3 times minus root 3, like that, so I'm going to have minus 5 root 3. It's not going to work. And then minus root 3 times that, it's going to be plus a 3. This is all over 6. That's not going to work. So maybe it was the plus 1. So 3 times 2 is 6. 3 times plus root 3 is plus 3 root 3. Minus root 3 times, that's going to be minus 2 root 3. And then that's going to be a negative 3. And this is all over 6. That and that makes a this, and that and that. Yeah. And so, yeah, we've actually covered all of the things here, because for different values of theta, different values of alpha, sorry, if I times this one, by 2 plus root 3, it's going to become the other one, and if I times this one by 2 minus root 3, it would be the other one, or whichever way. So that's fine. Yeah, I believe we've got all the solutions there. So actually, this isn't good enough. It's just that orange thing there. So this is messy. So we'll ignore this for now, because we can rewrite from the length equation to get all this stuff. Cool. All right then. Well, I think we're on question 6 now. Oh man, bloody, Jesus. All right, fine. Back in a minute. Right. Okay. Let's have black. So, A to the ant starts at point O on a plane, and at the start of each minute she chooses north, south, east or west and marches 1 metre in that direction. At the end of 2018 minutes she finds herself back at O. Let n be the number of possible journeys which she could have made. What is the highest power of 10 which divides n? Right. Okay. So, first of all, there's 2018 steps. Is that what's going on? This A to the n? Yeah, the start of each minute. Okay, 2018 steps. So, okay, I'm going to assume that A to the ant, right? An assumption would be that Ada is not near the north or south pole, because if she were, there'd be some funny things going on. For example, if I take this as a radial thing, and this is the North Pole here, and then I was to break this up as a grid system like so, like this, and I've got all the lines, the north-south lines popping out like this, then technically weird things happen when you're at the poles when you've got north and south directional things going on. For example, you could go south 1, so you could go south 1, and then say east 1, and then north 1, and you're actually back at the original North Pole, or wherever you were, or at the North Pole. And similarly, you can have a similar argument for the South Pole. I'm just going to assume this ant is nowhere near any of the poles, so that, I don't know, there's no funny things going on. So if I did that again, but nowhere near the poles, then if I did south 1, east 1, and then north 1, that just corresponds to just being one west away. And what that means is I can break this down into an XY coordinate plane problem. There's a whole branch of maths to do with funny stuff like that, with the North Pole, South Pole. I want to say it's steradians. It's not radians, it's steradians. There's a whole branch of navigational mathematics with that. To be honest, I don't think that question's banging on about that stuff, but I think Ada the ant is somewhere on the planet such that even if she takes 2018 steps purely north or purely south, yeah, you're not going to reach any of the poles. Yeah. So, first of all, if this ant starts and finishes at the original starting place, well, what does that mean? She finds herself back at O. So doesn't that mean the number of north steps equals the amount of south steps, and the number of east steps equal the number of west steps? So the steps in these directions must be the same. Okay. How can we generalize this though? Well, let's take this example here. So I went from 0, 0 to 0, minus 1 to minus 1, minus 1 to minus 1, 0. And then let's suppose I go backwards to 0, 0 again. So if I was to treat this in the x and y plane, then the sequence of steps I've gone is 0, 0, 0, minus 1, minus 1, minus 1, minus 1, 0, and then back to 0, 0. So from here to here, from there to there, from there to there, from there to there. So I've gone 1, 2, 3, 4 steps. So in actual fact, I don't need to include the origin in the original. I just assume that I'm going to be there, and I can just write these new coordinates as this is where you need to go next to. Okay. First of all, this should satisfy that there's an even amount of steps, which it does. There's 4 steps. You can probably tell from observation it has to be. And then, curiously enough, only either x or y differs by 1 at a time. So x and y can't both change, and if they did both change at the same time, then this would be a diagonal movement, and we're not allowed to do that. We can only move north, south, east and west. What else can be going on here? Now, I want to be able to write this as a unique thing. Why do I mean unique thing? Well, let's suppose I take this example and I go down here, right? Well, actually, aren't these unique enough as it is? I mean, this should be unique enough as they are. I'm just trying to think. Suppose we did this. So suppose we went south 1, then east, then north, and then let's suppose we went north again, and then east, and then south. So we're doing this. So we went north again, then east, then south, and then the final 2 is just going to be west, west. So it's now going to be back to there like that. So the problem is we've gone over the same point. It's not just the origin we've done twice. So what would that look like over here? Well, we wouldn't go to 0, 0 would be the next thing. We're at -1, 0, we're at -1, 1 because we've gone up to the top. Then we're at -2, 1, and then we're at -2, 0, and then we're at -1, 0, and then we're at 0, 0. So there's 1, 2, 3, 4, 5, 6, 7, 8 steps, because there's 1, 2, 3, 4, 5, 6, 7, 8 steps over to here. Okay, and the key thing is we've gone 1, 2, 3, so the third step here, 4, 5, 6, 7, the seventh step. Can we distinguish between these things? Well, not really. There doesn't seem to be a particular pattern. At the very least, though, I think an argument can be made that, well, the range of x can only be 1009. For example, if we had an x coordinate of, say, 50, which was the greatest x could have been in the x direction, then the lowest x could have been, would be what? Well, 1009 minus 50 is 959, isn't it? Negative 959. I think it's just a case of that. I think the fact we can have a range of 1009, because even if I was to go, say I was to go 50 in this direction, and then I went minus 959 in that direction, then even if I was to just boringly go in the x and y direction, I could go 50 that way, then minus 1009 backwards. Let's different colour it. You know, I'd go forward 50 and then back 1009 and then forward 959 to get back at the origin in terms of going left and right. I mean, as soon as we've got a maximum going in the x direction, we're going to have a minimum going there. So how are we going to build up combinations for this? Well, since the range is 1009, then for the x components, won't it just be 2018, choose 1009? And then for the y components, it's just going to be 2018, choose 1009. And then because they're independent, you're just going to have, because independence, for example, we could treat this as an up-down versus left-right. I mean, moving left or right in this problem doesn't necessarily change moving upwards and downwards. But then won't moving left and right restrict the amount of up and down moves you've got? No, that's fine. That's fine. So then what we've got, stick to the red, is we've got 2019, choose not 2000, choose 2000 and this is 18 up here. And then we've got the x times y, so it's squared, so we want to see how many times 10 goes into this. Okay, this isn't actually too bad, because this is 2018 times by 2017 times by so on and so on and so on and so on. And then this will be 1009 factorial, and this will all be over 1009 factorial times by 2018 okay, so it's 1009 factorial. So that goes and that goes. Right. So that's interesting. Interesting. So what's actually going to happen is all the even numbers in this factorial are going to cancel with this one. So actually, this thing squared is just going to be 2017 times by 2015. Is that right? You sure? Yeah, it's going to be all the odd ones. Are they? Yeah, that's right. It's going to be all of that stuff times by 2013 times by 321, and then it's going to be times by, well, there's a lot of 2's going on there. That's going to be 2 to the 1009, and then that's all squared. So really, I just have to think. Oh no, what's this 3 times 2 times 1 business? That's just 3 times 1. So the 2 goes. Oh no, is that a case? Oh, that's not going to be true, is it? This is going to be all over 1009 factorial, because there's no 2018 term. No, there is. Oh man. No, it doesn't go down as far. Oh man, I'm dropping the ball here. Right, so I'm going to have 2018. Okay. Times by 2017, times by, and so on and so on and so on. And then the last term up top is 1010. That's all being squared. And on the bottom, we've got 1009 factorial times by 1. So that's 1009 times by 1008 times by, and so on and so on. This is all squared. I don't know why I'm doing that. There's going to be a lot of 5s, isn't there? This is going to be quite a few. Right. Okay. that should be fine. Okay, so why am I such a... Okay, how many things are multiples of 5s of this thing up there? Well, from 1010 up to 2015, how many 5s are there? 2015 minus 1010, 5 minus that, nothing, nothing. 1 and 1005, that is 10,000, geez. 1005 divided by 5, 5s into that go 2, nothing, 1, 201. So what's that, 202 5s? Is that right? If I want the things from 1 to 10, I do 10 divided by 5, which gives 2. That's not including the 1 itself. Yeah, there's 200. Okay, so there's 202 5s at the top. So the top is going to be blah, 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 5 to the power of 202 on the top. And this is all squared. On the bottom, I've got the numbers from 1009 to 1. So really, that's 1005 down to 5, which is 1,000. 1,000 divided by 5 is 200. So there's going to be 201. So there's going to be 5 to the 201 times stuff going on here. For it to be divisible by 10, it needs to be 5. There needs to be multiples of 2 and 5. But since there's the numbers from 1010 up to 2018, I think we're going to have quite a lot of 2s. Okay, well 2018 minus 1010 is 8, nothing, nothing, 1. Divide that by 2, 1008 divided by 2 is 504. So there's times by 2 to the 504 on top. That's nice. And on the bottom, we've got 1008 minus 2, so it's 1006. Half that is 503. Ooh. Is that right? Oh my god, but there's some... Oh, I'm forgetting all the squares and the cubes and stuff. Okay, so there's 202 multiples of just 5 there. Then if I look at divisible by 25s, I think 2000 is the biggest, isn't it? Minus, and then 1025 is the next. So that's 5, 6, 9, 965. Wait, what? That's a 9. 975 divided by 25. 9. That's going to be a 3. Remainder 21. No. 22. So there's 40 of them there. So an extra 40 that are contributing from the 25s. Got 125s in there as well. So 125 times by 15. I think actually, we can fit a few. So 2,000 goes in there. So 2,000 divided by 125 is 16. 16 of them in there, but we're going up to 1,010. So there's 8 of them. So there's only 1,125, 1,250. So there's only going to be 8 contributing from there. Oh man, this is long. And what about 625? 625, or 2 lots of 625. 2 lots of 625, 1,250. And if I plus another 625, it's one. So there's going to be 2 popping out from there. So this is for the 1,010 up to 2018. I don't think I need to bother with the 2s actually. I think there's just going to be so many 2s because there's going to be 2s, 2 squareds, 2 cubes, 2 to the 4s, 2 to the 5s, 2 to the 6s. I think 2 to the 10 is 1,024. There's just going to be tons of them. And then if I want the numbers from 1 to 1,009 over there, well, divisible by 5, there's 201 of them. Is that right? Yeah. And then divided by 25, there's going to be a similar amount of them, isn't there? Because 1,000 divided by 25 is 40. Okay, so going to be a similar amount there. And then the amounts into 125 is going to be 8 as well. And then into 625, there's just 1, isn't there? Yeah, 1,000 divided by 125, there's 8 of them. But 1,000 divided by the 625, there's only 1 of them. So there's going to be an extra 1 from here. So there's an extra 1 there. These will cancel, and there's an extra 1 here. So in total, we're going to have a 5 squared times by 2 to the enough number over stuff times together, and this is going to be squared. So we're going to have a 5 to the 4 times by enough 2's over stuff, which means the most I can divide this by is 10 to the 4, which is 10,000. Jeez, yeah, tricky. Oh man, cancelling massive factorials. This isn't a good idea, by the way, because 69 factorial is essentially a 99-digit number. So 2018 factorial, you do not want to be calculating this out and figuring out what the last digit is. You're going to have a massive number. It's just best not to do it. All right, guys. Hopefully you enjoyed that. That was intense for me. But yeah, some questions really easy, some questions really hard. But yeah, toodaloo.